This is Mrs. O'Neill for AP Chemistry, Chapter 14, Section 1, Chemical Kinetics. Right here, I would pause the video and look over these terms, these words, because when you see them on the AP exam, you should think of this chapter, kinetics. Also look at page 596 in your book and make sure that those words become familiar to you. And some of them are similar to what you just read. Chemical reactions convert substances that have well-defined properties into other substances that have different properties. The chapter opening photograph you see here, for instance, shows that we watch complex reactions as they happen in time by observing the different colors of reactants and products. So in section 1, we're going to talk about the factors that affect reaction rates. Most of this is common sense, and you probably would be able to figure out that if you increase this, the rate of reaction is going to increase. But remember, we're talking about AP chemistry, so you have to use the terminology like collisions of molecules, things like that on your AP exam. You got to go above and beyond just going, oh, well, if we increase temperature, we're increasing the rate. Yeah, you probably can figure that out, and that's common sense, but you got to be able to give the why. So we're going to explore 4 variables that affect reaction rates: concentration, states of matter, temperature, and catalyst. And you're also going to learn that these factors can be understood, again, in terms of collisions among those reactant molecules. So the heat given off by the corrosion reaction of iron-magnesium alloy with salt water can produce a hot meal, especially for those that hunt, especially for those that go up and explore the moon like the astronauts. So this is really, really important. The rate of reaction is increased by adding salt water, so heat is produced rapidly. You will learn some ways in which the rate of reaction can be increased. Again, if you're interested in that hot meal, you want to produce it rather rapidly so that you get that meal to cook the way it's supposed to. So pause the video, fill in the blanks, and then play to hear my words. Ladies and gentlemen, the word kinetics just means rate, and the word rate just means how fast or the speed of reaction. So we need to know that we're talking about the speed of reaction when we're talking about kinetics and how fast they're going, but you also need to know the factors that affect them and how, the why. Can you explain in terms of AP terminology? So what does reaction really mean? Let's break up this word apart. We have re, meaning again or anew. We have action, state, process of doing. Again, manner in which such parts operate. So if we put these 2 words together to make reaction, we really mean a response to a stimulus or change or a transformation. So let's look at spontaneous reactions and how fast they actually occur. Well, silver will tarnish rather quickly. So lots of times I will take my cleaning cloth and maybe every 3 to 4 months, if I see some tarnish on a silver piece of jewelry I'm ready to wear, I'll clean it. No big deal. However, something like graphite, again, will turn into diamond on its own, but it will take several million years. That's a really, really long process. So I would consider the tarnishing of silver to be fast and the coal to diamond rather slow. However, again, chemists don't like that, right? They're more analytical, so they like to put a number associated with it, right? We want to know exactly how slow or exactly how fast. We want to know the rate of reaction. So the collision theory is that how fast the collisions are happening. Remember that a collision just means the reactants hitting each other and correctly at the correct orientation in order to produce those products. So the reactants colliding with each other in order to make those products. So this should make sense. If we heat up the temperature of that reaction, the reaction should go faster. But the why, can you put a good AP response to the why? One way to say it is the molecules have more energy. They've absorbed energy. Now they have more energy for the collisions. And if they have more energy for the collisions, they're moving around more. They're going to collide more often, producing those products more often. Higher concentration, same thing. If you have higher concentration, that means you have more molecules. If you have more molecules, those reactions are going to happen faster. If you have smaller particle size, well, if your particle size is smaller, that means you actually gained surface area. If you have more area for that reaction to occur, the reaction is going to be faster. So all of these things increase reaction rate. Again, we want to make sure we're understanding the why. So again, those 4 factors, kind of laying it out a little bit in more detail: physical state, concentration, temperature, and effect of or the presence of that catalyst, which does not play a part in the reaction at all. It is just added to speed up that reaction. Read this over, give it some thought, see if you can come up with the correct answer. And hopefully you did. So these are another way to look at reaction rates. Again, we're going to go through them step by step, so hopefully you understand the information. Nature of reactants, all we're talking about is the structure. So if we look at chlorine versus nitrogen, well, chlorine only has a single bond, so that's going to be rather weak. Very easy to break that one bond in between those 2 chlorine atoms. However, nitrogen is going to be a stronger bond, and you have 3 bonds to break. So the chlorine is going to be more reactive than the nitrogen. Concentration. Think about traffic. If you're driving along the road, right, and there's not too much traffic, you can just kind of mosey on over. But when you have a lot of cars and there's more traffic, there's going to be more chance for collisions. Even if it's just a little bumper, it's going to be more chance of that collision to happen. So the more reactants we have, the more molecules we have, the more chance for them to collide with each other, so the faster they can become products. Temperature, this should make sense as well. Why do we use the refrigerator? Well, let's think about milk. If you were to take your gallon of milk and leave it on the counter all day long, by the time you get home from school, that milk would be not so good. You probably have to throw it away. However, if you put the milk in the refrigerator, you can keep that milk in the refrigerator maybe a week or 2, and it's not going to go bad. So in this case, as you decrease the temperature of a reaction, you're going to slow down the rate of reaction. So obviously the opposite happens. Catalyst just lowers that activation energy. That activation energy should remind you of that energy diagram, that reaction diagram that I'm going to show you in a minute. So if it lowers the activation energy, that means it's going to increase the speed of reaction because you're lowering that hill. What do I mean by that? Well, here's an endothermic reaction diagram. Remember that your delta H would be negative. Here's your reactants, here's your products, and you need that amount of energy to get to this activated complex or this transition state in order to form those products. Well, what does a catalyst do? Just lowers that energy. Notice the amount of energy for reactants and the amount of energy needed for those products is the same, but it's how much energy to get over that hill. So if you are a car going up this hill, you are definitely going to get up this red hill or this lower hill much faster than going all the way up this one to reach the top or to reach the amount of energy to make those products. So if you're lowering the activation energy, that means you will be able to get to your products faster and you've increased your reaction rate. So pause the video, look over the graph, make sure that you can understand the graph, make sure that you can answer these questions correctly. Hopefully you got those answers. So surface area just means the more surface area, the more collisions. Again, let's give you an example. So here we have a cube, 1 centimeter in diameter all the way around. And if you notice over here, we are changing that one chunk into multiple pieces. So what I want you to concentrate here is how much surface area. So we started out with 6 centimeters squared. If we break it up into 8 pieces, it goes to 12 centimeters squared. 64 pieces, 24 centimeters squared. And if we break it up into 100, it goes to 60 meters squared. Okay, so we've actually even changed the unit there, just so you know. So obviously, the smaller the pieces, the more surface area you have. So it's going to increase the rate of reactions. There's going to be more spots, more places for the reaction to occur. So hopefully that makes sense. Here's a cool video on lycopodium powder.
This is a spore that's a really fine spore. Here, watch this. When we put it down here like this, you can kind of see when it comes out, that fine mist that's there. Well, by itself, it's no big deal at all. So I'm going to put a little bit here on the counter like this.
Okay.
And we'll try to light it on fire, and nothing will happen.
Just turns black.
No big deal.
Yep.
But when we disperse it through the air, so here, kind of watch this. So let me dump a little of that wax off. So here, watch this. As it's dispersed in the air, watch.
Woo! Oh, and it's
So
nice
it's
and warm.
just it's an amazing. so it goes up very quickly, but there's no fear of it jumping back into. Oh, there you go. That's a good.
Oh, that's
so
a
there's
good
no
one.
fear of it jumping back into here. So that's why special effects artists use this kind of material all the time. Again, a real fine spore called lycopodium. Special effects artists will use it like this. So here, watch. Here is a little
I'm so scared.
gadget. No, it's fine. A little gadget put together like this. So here, let me light it like this. Here, I'll hold on to it. Let me light it like this. In a little blow. Watch.
Yeah.
So
Whoa!
it gives you a nice little. Isn't that fun?
That is fun.
You ever seen the fire alarm go off here at 9 News? That's a pretty
Hopefully
exciting
we won't
thing.
today.
All right, let's take a look at this again, and our video editor is going to slow it down for us. So in real speed, again, what happens is the lycopodium powder goes inside the tube, and now all of a sudden when the air comes through, the lycopodium touches the fire, and we get the big fireball. The individual little grains of that lycopodium, that moss that's there, catches on fire because of all the oxygen around it. In slow motion at half speed, this is what it looks like. You can actually start to see a little of the lycopodium powder come out before it catches on fire. If we slow it down even a little bit more, you start to see that grain elevator kind of effect, where the fire literally chases the cloud of dust that's shooting out from the top. See, we're into 3 frames, finally 4 frames, and it takes off, and you get that massive fireball. Now remember, once again, the fire can't jump back and go through the tube. It has to be dispersed in the air for it to catch on fire. So it's one of the safe ways that a special effects artist is able to produce that great big huge fireball kind of effect.
Whoa!
So it gives you a nice little. Isn't that fun?
That is fun.
You ever seen the fire alarm go off here at 9 News? That's a pretty
Hopefully we
exciting
won't
thing.
today.
Well, hopefully you thought that was pretty cool. And I will see you in class.